So 22H is all about sets and Venn diagrams. Do you guys have some idea of what a Venn diagram is? Has anyone ever used a Venn diagram before? Like when? Like in English, you do? Yeah. What do you do?
For comparison between differences.
Oh, okay. Compare and contrast. That makes sense. So you probably have some understanding of what Venn diagrams are like. We will also talk about set notation as well today, or kind of revisit that a little bit. I know on your calendar it says H1 today and H2 tomorrow, but there really aren't any like separate notes for H2, so we're kind of going to do all of H today. Your stat box, if you haven't done your stat box already. And if you haven't got the title, it's back. So we'll also be getting some like new notation today as well. Starting here, we've got Venn diagrams, which are useful to represent events in a sample space. And with that set notation, there are a few things we're going to recall. So remember that U represents the sample space or universal set. So this whole rectangle is the sample set. So like if we were surveying the entire class, the whole rectangle would represent all of the students in the class. Keep in mind that this A prime is all the green stuff here, and that's the complement to A. So A prime is everything that's not A. So if my sample set was the class and I was surveying them and finding out if the students in my class were juniors or seniors, if A let A be juniors, then all the green stuff would be seniors. Everything that's not everyone that's actually in me, because I'm not a junior either. Right? So it's everything that's not whatever event A is. So here we've got some of that new notation. So A and B are different events. And if you have that upside down U symbol, that's the intersection of A and B. So this means right here, the intersection of A and B. And that contains all of the elements in common to both sets. So A and B are two different things, but this intersection, I like to think of it as the overlap. Like that's not a technical term, but so it helps me remember what's what. Is when I see that upside down U, I am thinking that's the overlap. So where A and B overlap, this is that part of that set. Now, we use set notation at the very beginning of the year, and so I've got this on the bottom here just as a reminder that the intersection of A and B are all the X, so that the X's are in A and in B. They have to be in both for this intersection. Any so far? So you'll definitely see the symbol when we talk about more events and different things in sections I and J. We will be using these symbols as well. So just we're learning what those symbols mean today. Now if you've got a right side up view, that's the union of both sets A and B. So this is the union of A and B. And that set contains all of the elements that are in A and in B and in both. So this union is going to be all of A, all of B, and it'll include that overlap. And you can notice, kind of like the last one was shaded in lavender, just the intersection. Here, the union is shaded in lavender with all those different parts. Is there any weirdness or any confusion about the difference between intersection and union? So we've got one more type of set to take a look at. We'll do a little example, hit the stop box, and then one last example, and we'll be all done. So the last set is a disjointed set. So disjointed sets have no elements in common. So we've got A and B. Notice they're not overlapping at all. So the intersection, the overlap, doesn't exist. So that's called the empty set because there is nothing that is in this overlap. They don't overlap whatsoever. Another term for this would be that the events are mutually exclusive. The first thing we're going to do is identify and shade in these different sets just so we get more familiar with them and what they look like on our Venn diagrams. Then we'll actually do some probability with them. So here's our first example. It is directly out of your textbook if you would like to look at it. And it's the diagram that represents the most general case for three events happening in the same sample space. So this kicks it up a notch. You've got three different events, A, B, and C, in our sample space U. So you'll see the two different events, but you might occasionally see the three different events here. So on separate Venn diagram sketches, we're going to shade in these different parts. We'll shade in A, complement of B, the intersection of B and C, and the union of A and C. I would recommend for your notes to write 4 different diagrams. I'm going to erase, because I've got the smartboard up here, and shade all these in. So if I'm shading in A, what do I have to shade in? The whole A circle. Alright, so this is A for part A. That whole A circle is what's in A. So anything in this circle will be that event, whatever that happens to be. So we got some people still writing, so I want to give you guys a chance to catch up before we go on to the next part. So then for B, part B that is, so part B is the complement of B. So remember, that means not B. So I have to shade in everything that is not in the circle of B. So I've got to shade in all of this, all this. So I'm shading in everything that's not B. We clear on that one? So then we have to shade the intersection of B and C. So remember, this is the overlap. That upside down U is the intersection, so that's the overlap. So that's where the circle for B and the circle for C overlap, which will be this shape right here. One more, so that's the not the intersection, the union of A and C. So remember the one that looks like a U is union, and that is everything that's in A and everything that's in C. So I can do this part, that whole circle. I can also do this whole circle for C. So it includes the overlap and just A and C. So those are just some basics. You will have some on your assignment with like the two Venn diagrams that you can practice these. If you look at the success criteria over here, you know, there are different versions too where it's not always just like the circles. You might have the union of A and the complement of B or something like that, and have to think about those things as well. Also, when we get into sections I and J, there will be some more like formulas and probability laws and things. So it does help to understand what these symbols look like on a Venn diagram. So we're going to hit up that stat box, and then we're going to do one last example with probability. But I guess you can see that I can't stress enough. Whatever words you can write in your stat box so that you know the difference between union and intersection, I would jot that down. Because the symbols look really similar, right? Yes, one's upside down, but they look really similar. So here's the first part of the last example. A survey of 32 students found that 20 students enjoy Skittles, 8 like Skittles and M&Ms, and 3 would not like either candy. So the first thing we're going to do is display this information in a Venn diagram. Give you guys a chance to write that down before we start going through this. So when we draw the Venn diagram, actually, I'm gonna scooch it over a little bit here. What does this rectangle represent? The what? The whole set. All of the kids in the survey. So 32 people are in that whole set. So then we have two different events. What are the two events that we have? M&Ms and Skittles. So I've got M&Ms and Skittles, and I know that some kids like both. So I can fill that in. 18 students like Skittles and M&Ms, so I can put the 18 in that overlap area. That's the intersection of M&Ms and Skittles. 3 do not like either candy. So 3 kids in this class were like, nope, I don't like M&Ms and I don't like Skittles. Where does that 3 go? Yeah, outside the circle. Somewhere still in our box, because they're still in the class. They were still part of the survey, but they don't like Skittles, they don't like M&Ms, so they're outside of those circles. In order for us to finish up, we have to figure out how many students only like M&Ms and how many students only like Skittles. Well, how many total students like Skittles?
20.
So if I take 20, which should be this whole circle here, the Skittles circle has to add up to 20. I can take 20, I can take away the 18 that like both, and find out that 2 students only like Skittles and don't like M&Ms. So I want to make sure that we're all on the same page. We still have one more piece to do, but with this stuff, I find it difficult to do like a step-by-step list of like, well, then subtract this or add this. But if we think about it, this whole Skittles circle right here has to add up to 20. So if I subtract the 18 that are in the middle, there are 2 left over that only like Skittles. So how many students only like M&Ms? How did you guys get 9? What was that? That's all that's left. So to further explain what Michael said, there's 32 kids in here. So if I take 32 and I subtract the 18 that like both, I subtract the 2 that only like Skittles, and I subtract the 3 that don't like any, I end up with 9 left over. And it doesn't hurt to double check to make sure that all of this adds up to 32, but that's where we got it. So 9 students only like M&Ms. Okay, we're going to keep this Venn diagram in order to answer a few probability questions. I feel like I want to change one of the questions, but maybe I shouldn't. I'll just leave it. Okay. So we're going to determine the probability that a randomly selected student, and we've got a few different things that we are going to do. I think I meant to say likes M&Ms, and then I typed likes only. That's okay. So we'll roll with this. So we know that probability is when we take the chance that the event happens over the total different events, the whole sample space. So I know that there are 32 students. So how many students only like M&Ms? So it's 9 over 32. Because I can't reduce it. You can get a decimal if you want. Now what if I just said, let's determine the probability that a randomly selected student likes M&Ms. What would we have in the numerator then? What was that? That's 18 that's M&Ms and Skittles, but I'd have to do this whole thing.
27.
So I'd have 27, right? If it just said likes M&Ms, that'd be 27 over 32. I wanted to show that, but that's not what I typed up. That's okay. And we can't reduce that one either. Alright, now, so if we're on to part B, is that where you were already on part B? So, what's the probability that a randomly selected student likes both types of candy? Well, how many students are in my overlap here? 18. So that one would be 18. Like that, pink on pink's not a good idea here. 18 over 32. Now I can reduce this one to 9/16. So those are the chances that a randomly selected student would like both kinds of candy. And then the last question is, what is the probability that a randomly selected student likes only M&Ms or Skittles, but not both?
11.
How'd you get 11? All right, I'm going to have to add the students that like M&Ms only and the students that like Skittles only. So I end up with 11 then over 32. Again, we can't reduce that one. What do you guys think about these Venn diagrams? They're easy? Okay, I felt when I first looked at them, I was a little bit like, what's going on? But the more you work with it, I think you'll be all right. Keep in mind, you want to ask questions if you've got them. And are there any? Okay. Well, I found them to be pretty helpful. Like, kind of like, I felt, I guess, the same way about tree diagrams, where at first I was like, no, I hate this. And then when I started making them, I'm like, okay, well, I kind of see the point.
Yeah.
I see where it's helpful. I didn't hate this, but I can see how it is helpful for us. So as I mentioned, there are not any separate notes for H.2. Give it a shot. Let me know if you have questions on it.